Hello everyone, and welcome back to the channel. Today we are going deep into one of the most extreme railway construction stories on Earth. The Hotan-Ruoqiang Railway, also known as the Harshest Railway, a line built across the edge of the Taklamakan Desert in Xinjiang, China.
Before we begin, if you love mega construction projects, impossible engineering, railways, bridges,
tunnels, airports, and the hidden technology behind the world's biggest infrastructure.
Make sure to follow the channel, hit subscribe, and turn on notifications. Because what you are about to see is not just a railway, it is a battle between human engineering and one of the harshest deserts
On the planet. The Taklamakan Desert is one of the largest shifting sand deserts in the world.
It is dry, remote, windy, and brutal. Sandstorms can bury roads, damage equipment, cover tracks, and erase construction paths almost overnight. Building a railway here was not as simple as laying steel rails across the sand. Engineers first had to ask one critical question: how do you build a permanent railway in a place where the ground itself keeps moving? The answer was a carefully planned desert-resistant railway system,
A combination of anti-sand barriers, straw checkerboard grids, drip-irrigated shelter belts,
wrapped core desert subgrade, and long elevated oversand viaducts designed to let wind-blown sand pass underneath.
The project began with survey teams entering the empty desert. Before any heavy construction could start,
Engineers had to mark the exact railway alignment across vast, golden sand flats and rolling dunes. Temporary service roads were built beside the future track, so trucks, cranes, excavators, drilling rigs, and workers
Could reach the remote construction zone. But the first major construction task was not the railway itself.
it was protection. Crews installed outer sand barriers and intermediate sand fences along both sides of the future railway corridor. These barriers acted as the first defense against drifting sand.
Then came one of the most recognizable desert engineering techniques: straw checkerboard grids. Workers pressed straw into the sand
In thousands of square patterns, creating a rough grid over the desert surface.
These grids slowed the wind, trapped loose sand, and stabilized the ground. Next, the project added water. In this dry environment, planting a shelter belt was impossible without irrigation.
Engineers drilled groundwater wells, installed well casings, tested pumps, laid main irrigation pipelines, connected branch pipes, and arranged drip lines through the checkerboard fields. Only after this hidden water network was ready could workers plant rows of desert-tolerant shrubs. These young shrubs were small at first, but they were vital. Over time, they would form a living, green-gray shelter belt, protecting the railway from wind and moving sand. This was not decoration, it was infrastructure. Only after the anti-sand system was in place did crews begin building the railway formation itself.
The central railway strip was cleared and graded. Layers of fill were placed, leveled, watered, compacted, tested, and repaired.
Engineers built a special wrapped core subgrade. Local desert sand formed the inner core, while more stable granular material wrapped the sides, creating a stronger, controlled railway bed suitable for the desert environment.
But in the most dangerous dune crossing zones, even a strong embankment was not enough. There, engineers built oversand bridges, point-long elevated viaducts supported by evenly spaced concrete piers. These bridges raised the railway above the moving sand,
allowing wind and sand to pass beneath the structure instead of piling up against the track. The bridge construction followed a precise sequence. First, survey crews marked pier foundation points across the dunes.
Then, workers leveled small pads, excavated foundation pits, installed rebar cages, poured concrete footings,
and inspected each base. Prefabricated concrete pier segments were transported into the desert by heavy trucks.
Lifted by cranes, stacked, aligned, braced, and secured.
Once the pier row was complete, cranes installed pier caps, then long prefabricated concrete girders. Slowly, span by span, a skeleton of the oversand viaduct stretched across the desert. After that came the bridge deck. Crews installed temporary work platforms, formwork, reinforcement steel, and poured the concrete deck slab. The deck was cured under the harsh desert sun.
Inspected, repaired, and fitted with low-maintenance railings. The structure was now ready to carry the railway track.
Then the track building phase began. Crushed stone ballast was delivered, spread, leveled, and compacted. Concrete sleepers were staged and placed at exact intervals. Workers inspected spacing, alignment, and height. Before long, steel rails were delivered to the site. The rails were pulled into position, seated onto the sleepers, adjusted to the correct gauge, fastened with clips, welded into continuous rail, ground smooth, and finally tamped into correct geometry. At this stage, the desert railway had become physically recognizable. Ballast, sleepers, rails, viaduct, subgrade,
and protection systems all working together. But a railway is not complete until it can be controlled safely.
Signal cabinets, cable conduits, trackside sensors, signal masts, maintenance shelters, protective fencing, and access gates were installed along the corridor. Technicians pulled cables, tested circuits, checked grounding, activated systems, and verified communication links. The line was still closed, but it was now becoming a functioning railway system. Before any real operation, the railway had to prove itself. First came walking inspections. Then a small inspection vehicle moved slowly onto the rails. Engineers watched the track, bridge, ballast, sensors, and signals. After minor corrections, a heavier engineering test train crossed the oversand viaduct, applying real load to the structure. More inspections followed. Then came controlled trial runs. A trial train moved slowly across the desert section, then later at a moderate speed. Sensors monitored vibration, ride quality, rail performance, signal response, and bridge behavior. Every stage had to pass before the railway could move toward operation.
And finally, after construction, correction, testing, and commissioning,
a modern train now travels across a line that cuts through one of the most hostile desert environments on Earth. Beneath it are rails, sleepers, ballast, viaducts, concrete piers, and engineered subgrade. Around it are straw checkerboards, sand barriers, irrigation lines, young shelter belts, service roads, signal systems, and maintenance infrastructure. This railway is not just a transportation project. It is a complete desert survival system. It connects remote regions, strengthens the railway network around the Taklamakan Desert, and proves that with enough planning, engineering, and patience, even shifting sand can be crossed. From empty desert to sand control grids, to subgrade, to oversand bridges, to rails, to trial trains, and finally, to operation. The Hotan-Ruoqiang Railway is a powerful example of how modern infrastructure can overcome extreme geography. If you enjoyed this construction journey,
don't forget to follow the channel, subscribe, and turn on notifications for more mega projects from around the world.
In the next video, we will uncover another impossible engineering story: how humans build where nature says they shouldn't. Thanks for watching, and I'll see you in the next one.